of chapter 3, the notion of vectors. What is a vector? Okay, so let's start off by getting to vectors in a mathematical / physical form by talking what they are with respect to coordinate systems. We're going to get to introduce our concept of vectors by coordinate systems. Okay. Let's start off with the coordinate plane, you know, the x, y, and we're going to go to z when we talk about three-dimensional vectors and yada, yada, which is what we must do eventually. But right now, we're keeping it simple with the plane, xy plane. Okay, random, okay, x, y, and we have it, and we have all these points. So we call the points in the plane, they're called rectangular coordinates, but more or less they're defined by rectangular coordinates, and x and y coordinates are these points. Rectangular or Cartesian coordinates, as you know, after Rene Descartes, you know, that sort of thing. You know that from your algebra 1, you know, your x, y. Okay. So another way to represent a point is we can go from Cartesian coordinates, x, y, z, w, whatever, into polar coordinates. And then after that, you know, to represent in terms of angles. It's going to be very important when we go from linear kinematics, xy kinematics equations, into rotational kinematics. So everything's going to be in terms of r and theta. You know, you've seen polar coordinates already. And then when we go to other geometries, like your cylindrical systems or your spherical systems, those take on even more coordinate systems. In cylinders, we have the cylindrical coordinate system, and then in the spheres, we have the spherical coordinate system, and so on and so forth, depending on the geometry. And we usually, the geometry is going to be linear, rectangular, which is basically the same Cartesian coordinates, and then cylindrical, and then we can go to spherical. And so when I introduce quantum mechanics way down the road, we're going to go to a spherical coordinate system. And so that we can define how a sphere is defined by, well, a radius, it has size, it has a rotation angle, and it has a precession angle. So it can bob up and down, back and forth, or top to bottom, and also rotate, and it has shape. So it's going to be 3 coordinates that define the spherical coordinate system. That's later on. Another way to represent a point is plane polar coordinates. You've seen these in algebra, I hope by now. Or are you getting geometry? Sure. So normally r is the distance or the radius. Yeah. So distance from the origin in this, you know, xy system, and theta is going to be the angle between a fixed axis and the origin to that point. So I'll origin to that point. And hopefully you have that from writing too fast, moving too fast. Tell me to stop, I'll scroll on up. So let's consider a point from the x-axis. Our angles are going to conventionally be defined from the x-axis. We can look at things from the y-axis, but just by convention, we establish standards. We say by convention, it's usually accepted as that's a standard. The SI units are the standard system that we use. We don't have to use System International. That's the standard. Let's consider a point from the x-axis. We have an XY coordinate system this way, and we have a distance from the origin we call r, and this is theta. And this P here is for our point. And again, theta is angle. Come on, angle from the x-axis. R is this radial distance. Sorry about that. Okay. Radial distance from the origin. And this point, as I mentioned, this point P is going to be defined in terms of the polar coordinates r and theta. Far so good? So hopefully that's all news. I want to do that. I want to insert a new page. Okay. So the angle theta, as we know, is going to be measured counterclockwise. That's our unit circle. It goes the other way against the clock. Zero degrees is the positive x-axis. The positive y-axis, that's 90, then 180, 270, 360. So counterclockwise. And let's see that a little bit more in terms of some geometry here. So drawing a right triangle. X, R, Y, and X. And then we can define X and Y and R in terms of trigonometric identities. Cosine, sine, your tangent, and the inverses when needed. For example, straight up, we can say cosine theta, adjacent over hypotenuse. So we have X over R, and then sine theta, the Y over R. Therefore, if we want to figure out the value of X, and then we have that. And tangent is just, opposite over adjacent, sine over cosine. Y over X. Let's see.
Mr. Kelly, would you mind pausing for 1 second and scrolling up? I missed the, perfect.
Mm-hmm.
Mr.
Okay.
Kelly,
Yes.
We use the polar coordinates when a thing is not moving in like a horizontal or vertical manner, right?
It's rotating, yeah. Or we're going about the XY plane in a circle. That's pretty much the reason why when we use polar coordinates is when we're rotating. That makes sense. We're not just going along the x-axis or going along the y-axis. We're actually spinning or going in a unit circle.
I see. Yeah.
Yeah, and then the r's cancel out, sine, cosine, cotangent, do all that nice stuff. Now the magnitude or the value of r is just going to be the Pythagorean theorem, and that's what we know in math, and then we need to take that same mathematical idea and translate that to a physical idea when we're trying to find the value or the magnitude of a vector. The value or magnitude of a vector will be the Pythagorean theorem, the square of its sums, the square root of the square of its sums. Just like in Pythagorean theorem, basic x squared plus y squared. Well, we know that r squared is x squared plus y squared. So this is just the trigonometry, geometry background that we're going to need to translate up to physics. So that's the gist of section 3.1. Then if we venture into 3.2, we've already talked about this at length, and now we're going to bring it all to home in chapter 3, 4, but definitely by 5 when we get into forces, where we're going to need to understand, okay, well, we have this force. This force is going to be at a particular angle, just like r is at a particular polar angle. Now we have to figure out all the forces that are moving in the x-axis, all the forces in the y-axis, all from this idea of vectors, right? So that's why it's important to understand the math background before we get to the rest of physics. So vector and scalar quantities. Know this already. Scalars are just numbers. No direction. Vectors are quantities. Magnitude and direction, but I do like to just say number and a direction, or number and a sign. Right, so i.e. plus minus 5 meters, whereas a scalar would just be 5 vectors there. Okay, so that's just rehash the definition. 3.3, vector properties. So now what we really have to understand the difference between parallel vectors, anti-parallel, adding and subtracting vectors. So we'll be dealing with that. Let's say we have two vectors and we want to see if they're equal or not. Well, two vectors are equal. Let's say vector A equal to vector B. The arrow denotes direction. A and B is the size. That's just the abstract. So A is equal to B if the size and, if the size and direction are the same, they're parallel. Now, anti-parallel would not be equal because the directions are opposite, right? So are the same. I.e. parallel lines of equal size and direction. Vectorially, they're different. Magnitude, size-wise, and two vectors that are anti-parallel or opposite would have the same value. They can, but if the directions are unequal, opposite, then the vector is unequal. So they have to have both, same size, same direction. Quick picture of that. So we have A and B in this coordinate system. Questions on that? Seems okay. And these were two scalars, obviously, equal. Again, as I was saying, the anti-parallel, the scalar value, 5 and -5, they'd be the equal in magnitude, but directions are different. So what about adding vectors? And I think that'll be probably the close for us today, and then we'll continue with that more for next time. So if we want to add vectors A and B, we have to be careful about it. They don't add like numbers. They can sometimes. But most of the times, in generality, we don't add vectors like numbers because those vectors, like this A and B here, they have parts to them that we have to consider accurately. And so when you do that, you can't, treat them as if they're numbers. Well, by nature, they're not numbers anyway. So there's a special way of adding vectors. So if you add vectors A and B, right, I use a simple method called the tip to tail method. Let's see what that looks like. Parentheses. Age-old method. So for example, when you add A and B, then you're going to get a value called the resultant, R. Okay? R is the result. Resultant vector of A and B's addition. Now let's say we had a particular configuration of A and B. Let's say that A moved parallel to the x-axis, and let's say that B was arbitrary in space, and let's say B is hanging out like so, like that, and this is A. Well, adding them together geometrically and then mathematically, we'll see. But geometrically, we have to take the tip of A and attach it to the tail of B vector, and then draw the resultant vector from A to B, because that geometrically is signifying the sum of A to B. So let's see what that looks like. So the A vector here, tip of A attached to the tail of B, and the resultant would just be not hypotenuse, but that line here, from a scaling triangle in this case, but that is the geometry of the addition of A to B. Any questions on that? Again, that's the geometry and math we just saw. Okay, so last quick example. Let's say we had A was at some arbitrary angle like so, and B is just out there in space, and we want to add them together. Well, then same method, we just say A to, as best we can, B. Again, this will be, we don't have to be so much accurate now because we're not going to be adding them geometrically or using like graph paper to draw these lines correct. But this is the general form. The tip of A is going to be to the tail of B, and then we just draw the resultant vector from A all the way to B. And so we have a different configuration. And so we'll get into more of this, vectors and their components, next time.
Wait, Mr. Kelly, question.
Yeah.
Does the distance of the actual vectors themselves, are they both between the same amount of time?
We're not even
Like A's like the distance of the vector A is between time A and time B, and the distance between vector B, is that with the same time, or is that within the same time?
No, don't think about time. This is all geometry at this point.
Oh, okay.
Okay. So, okay, I'll see you guys in 10 minutes. Don't show up for, your test corrections. See you at 2:30.